repeat. Tomorrow's tutorial, we will be comparing convergence using approach 1 versus approach 2. Simple biasing and resistive divider biasing is very sensitive to supply voltage variation, beta variation, resistor variation. For supply voltage variation, we will consider plus minus 10% supply voltage variation, beta variation plus minus 50% variation, resistor variation plus minus 20% variation, because the tolerance band maximum, all of you, how many of you remember that it can be plus minus 20, right? What you studied last time, last semester in Introduction to Electronics lab? Hello? Anyone? Do you remember the resistor tolerance?
Yes, sir.
So how much was it?
So usually it's 5, 10 or 20%.
So 5% for which case? What is the band?
Gold.
And 20%?
No band.
Okay. So that means we'll do this. So this is one thing. Simple biasing and resistor divider biasing. We will analyze this. And then we will show that with resistive divider biasing, resistive divider biasing with emitter degeneration is very robust and hardly sensitive to any of the above variations. Shruti, can you set up a meeting at in our TA thing at around 3 p.m. We will discuss we'll involve all of them. We'll discuss who will solve which ones. Okay, so it will be 1.5 hours. I'm thinking half an hour for this, and this thing half hour, and I would say this is, I think, 45 minutes. I would rather say 45 minutes. 15 minutes for the 3 cases. So 45 minutes. So 45 minutes. And this should be 15 minutes, because this will be a follow-up on this thing. You will replace this with any of the, we'll solve one case only. Beta variation is enough to solve it. Okay. So Shruti, make a note of this. I don't know if Abruti is there, and Rakesh also, please call them to join, so that that part, because I want to finish this amplifier by at least the amplifier topologies by next Wednesday. Okay. Okay. So now, so what we will do is, any questions from yesterday?
Sir.
Yes.
Can you go the previous page you shown first?
Yes. Tell me. Yes, go ahead. Hello. What did you want to say? Rishabh, you asked me this question. Yes, sir. What? Yes, Rishabh, please tell me, what is it?
Sir, VTS you connected from the downside. If you connect it from VCC, like the arrow is shown, it connected from VCC. Then VTS will calculate from R2 divided by
VTH is the Thevenin voltage, right?
Yes, sir.
So now, what is the definition of Thevenin voltage? Open circuit voltage, right?
Yes.
So here, what is the Thevenin voltage at this node X? VCC divided by
R1 plus R2 into
R1 plus
R1.
R2 times R2, right? Open circuit voltage.
Yeah.
And R Thevenin is what? What is the resistance looking into this point? What is the Thevenin resistance? When you do the Thevenin resistance, you short all DC voltages, open all AC DC currents, right? And apply a voltage at that point and measure the current, and that is your Thevenin resistance. Right? Open circuit resistance, if you want to call that way. I mean, there is nothing called an open circuit resistance like that, but that is the resistance that you see looking into that node. That is the Thevenin resistance.
So, sir, you calculated the Thevenin voltage and resistance from ground to X point.
Yeah, because we want to find out what do we want to find out? See, when in the case 2, if I1 and IB are of similar order, I've given the definition of order here, right? I've given the definition of order here. So if they're of similar order, that means I cannot say that Vx equal to this voltage, right? Because this current, there will be some current here, which is a summation of this current plus the base current. So I have to use the Thevenin equivalent model to solve it. Am I clear?
Yes, sir. But if you connect VTH from the upper side, like if you calculate like that
What
way.
do you mean VTH from the upper side? I don't understand that concept there.
Like if we connect VTH in place of R1 and make the circuit like that.
No, I didn't understand. What is the meaning of VTH connected from R1? You have to explain that to me. Thevenin voltage has nothing, there is no connection there. It is a Thevenin voltage at this point. Suppose I have a circuit here. R1, R2, R3, and there is an RL. I will tell you to find the current flowing through RL. What will you do? You will find the open circuit. What is the Thevenin voltage? Well, you will model this circuit. So I think your network concept is messed up. So if I tell you, I don't know if it is the same with not only him, but it could be that it's messed up with others also. R1, R2, R3, and I want to find the current through RL. V1. I want to find how much is IL. I can write case loop equations and do it, but I can do using Thevenin. So I can model this. This is equivalent to VTH followed by RTH, which is a Thevenin model, and then I can put an RL. Now, what is the definition of VTH? VTH is I remove this circuit, this resistance from here, the load. Okay, I remove this load and find out the open circuit voltage. Right? So what is the open circuit voltage? VTH equal to R2 divided by R1 plus R2 times V1. Then I have to find RTH. What is RTH? RTH is an R1, R2. I short this V1, R1, R2, and R3, and I apply a test voltage Vx, measure this Ix. And this will come out to be RTH equal to R3 plus R1 parallel R2, right? This is the method. So now we have to apply the Thevenin concept over here. It is simple. I have to apply a Thevenin here. My load is here. This is the load current I want to find. What is IB? That is the load current. So if I want to find this IB, the V1 is in VCC here, R1, R2, and something the load current. I remove the load, apply the Thevenin voltage. So is that isn't that how you did it last semester?
Yes, sir. Okay.
No. So don't get don't see you are bold enough to speak up. Okay, so I appreciate it, but I'm sure there will be another 60%, another 60 to 70 people who are just sitting there who do not still understand and are not speaking up. So Rishabh, I really thank you for speaking up and asking this. Now, is there anything that I'm missing in the explanation? because I didn't want to go into basic network theory. See, the thing is, when I1 and IB are of the same order, I cannot neglect this current flowing over here. So my load is here. Thevenin as a model says that I can remove the load, measure the Thevenin, I can model it like here RTH, VTH, okay, and then the load RL. In our case, the load here is this transistor base current. It's a different load, not an explicit resistive load, right? So I can do. So what is the Norton equivalent here? Anybody? How do I do the Norton equivalent, which will be equal to IN parallel RN and RL, right? Correct? Yes or no? Come on, guys.
Yes, sir.
Right. So how will you, what is the definition of IN at that point?
Short circuit current.
Short circuit and find the current.
Yes. So what you do is you short this current, you find ISC, which is equal to IN. What is RN? Same as what it was, RN will be equal to RTH, right? Am I clear? Show it.
Yes, sir.
Okay. So how many see? I'm assuming that you know Thevenin Norton, and I'm not. I did not go into delve into this thing. Why I did this Thevenin equivalent, Norton equivalent? Why it was like this? I hope is it clear. So if it is not, then please stop me and let's analyze it. Okay, so let me see how many of you can do. I'll just give a variation of that problem. Somebody biased a transistor like this. R1, R2, R3. Sorry, there is no. This is a short. Okay, so I haven't gone into that yet. RL, RC. Okay, VCC. What is Vx? If IB is not negligible compared to any of the currents flowing in R1, R2, and R3. Can you tell me? Guys? Okay, so Shruti, please take a note of it. Tomorrow in the tutorial, we might solve this. So please analyze this. Analyze this. Okay, so that means this will be modeled as VTH, RTH, RC, VCC. So they should be modeled like this because my load is here. I want to find the load current. I mean, that is how I treat it as a load, and I'll use the Thevenin model to do that. Thevenin equivalent circuit. Okay. Am I clear? Is that clear?
Yes,
Okay. So, who said yes right now? Who is that yes?
sir, it's me.
Okay. Now, Harika, right?
Yes, sir.
Okay. Did you have the same doubt as Rishabh had? Don't hesitate.
No, sir, I didn't have.
Okay. Rishabh, am I clear now?
Yes, sir.
Okay. So those who remember that there is a saying like if you think that you will be considered stupid if you ask a question in the class, okay, and do not ask a question, you will remain stupid forever. it is better to look stupid now and be smarter later on. Okay, so please take that, and there is no harm uh, in asking a question, and because then I have to go back and explain it. Okay. Okay, so now we'll talk about another biasing scheme called um, uh, resistor divider with emitter degeneration. Okay. Now, before that, let me quickly illustrate why this is required. Okay. Now, why is this required? So let us try to take a simple case. Okay. I will solve a simple case in front of you. So let's see. Yes. So all of you, this is one of the problems in the textbook. R2, R1. This is 17 kilo ohms. This is 8 kilo ohms. Okay. This is 2.5 volts. Okay. And this is RC equal to 5 kilo ohms. Okay. So now we'll use a let's assume IB is much smaller than I1. Thus I1 equal to 2.5 divided by 17 plus 8 kilo ohms equal to 1 milliamp, right? No, 100 microamps, sorry, 100 microamps. Equal to 100 microamps. Thereby, Vx, this node, implying Vx equal to 8 kilo ohms times 100 microamp equal to 800 millivolts. Okay, is that clear? So if this is 800 millivolts, then I can find out, therefore, IC will be equal to IS e to the power of VBE by thermal voltage, and IS is given already in the problem as IS equal to 10 to the power minus 17 amperes, and the beta of the transistor is given as 100. Okay, so now based on this, what is the value of IC? IC equal to how much? Can you guys solve it? Use thermal voltage as 26 millivolts or something, or you can use the exact expression KT over Q. Anyone tell me how much is IC? Anybody?
0.231 milliampere.
Okay, so good. So 231. Subhayan Nath. Okay, 231 microamp. Okay. So therefore, IB is going to be 2.31 microamp. Correct? Now clearly 2.31 microamp is 1 by 50 of this roughly, which is roughly equal to 1 by 50 of I1. So our assumption is correct. So assumption is correct. Okay. So that means it is okay. Everything looks okay here. Now, we get this thing IC and this thing. Now, so Subhayan had built this thing and designed it, and therefore what is the VCE? V out DC voltage equal to how much? So 2.5 volts minus 231 micro times 5 kilo ohms. How much is that? 1.345 volts. Correct? Yes or no? So Shubhayan designed this circuit, which is pretty close to half of supply voltage, keep in mind. Okay, so I designed the circuit and it is pretty close to this value. Okay, so now if I have this V out equal to, and we know that this enters into saturation or comes out of forward active mode if this voltage reaches minimum volt V out min that it can reach without but still maintaining it in forward active mode, V out min equal to 0.2 volts. We have said that VCE sat equal to 0.2 volts. So therefore, this node, the output voltage, if I have Subhayan built a very nice circuit, so the DC voltage is 1.345 volts. And the signal can go down all the way. He tries trying to amplify a sine wave. He applies a certain sine wave. The output voltage here is going to swing all the way down to 0.2 volts beautifully. Okay. So it comes down by roughly 1.1 volts and it goes all the way up to 2.4 volts. Okay. It's a nice sine wave he's getting. He's happy. And he sold this thing to his friend, who used it for quite some time, and then suddenly this transistor burns out. Okay, and this circuit is out of the warranty period for Shubhayan gave. So it is out of warranty. So he said, yeah, it worked for this many 1 year. Now you're on your own. So now one of your friend goes and finds a transistor, and what he found out is that he's getting, when he plugs in this, he found a transistor whose beta equal to 50. Okay, he found the transistor has a beta equal to 50. So as soon as he plugs this transistor into that PCB, he solders it down. And then what happens? Can you guys tell me what will happen when he replaces this with a new transistor whose beta is equal to 50? Can you tell me that? Can you please solve what will be the, what do you have to solve? You have to solve, the IC will stay at IS, let us say, is maintained at that value. Okay. No, IS is, so he comes up with a beta of 50. No, that is going to, no. So beta of 50 and has an IS equal to 2 into 10 to the power minus 17 amperes. Okay, so because the transistor is characterized by the beta and the IS, so he buys a transistor whose reverse saturation current is 2 into 10 to the power minus 17 and beta equal to 50. Okay, so then can you tell me what will be the output voltage, DC output voltage? Will it perform as well as it was performing before? Can you tell me that? Will it give you a swing of almost 2.2 volts? Is the question clear to all of you? Am I clear with the question?
So
Yes.
I had a question about an earlier part of this question.
Okay.
We got the lower swing as 0.2 when the transistor enters into saturation. How did we get the upper value of 2.4?
No, it will be equal, right? Whatever is coming down, I just made it, said that let it be 1.1. Okay. So it is 1.145. Okay.
Okay. Fine. It's
So then
always
you can add equally. It should swing from this point equally up and down. I just approximated it. Good point, you raised it. So there is a numerical accuracy here. 4, 5 should be added, right? Then you are happy.
Yeah. Thank you, sir.
Okay. 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 So now please tell me what happens to the bias voltage V out DC voltage, and will the guy whom Shubhayan sold this thing, will he be able to get the same swing? That means will his headphone work with the same volume, or will the headphone will have lesser volume?
Sir,
Because the swing defines the. Sorry?
it's already in saturation.
No. What is the DC voltage you are getting now?
0.19 volts.
0.19.
195. 0.19.
It is already in saturation. That's why I made this IS a little different. It is already in saturation. It comes out of forward active mode. That's it. The amplifier is dead. Okay. So then this guy whom Subhayan sold gets super angry. He goes and reads up the textbook and he says that, you know what, Subhayan, you messed up. Okay. You should have done this. And then he modifies it. Subhayan, I'm taking your name as an example, so don't think that you are the guy, okay? You are the character in this play at this point. Okay? Subhayan, you're hearing or you took offense on this?
No, sir, I'm hearing.
Okay, good. Okay. So then, tell me your friend's name, anybody's name whom you sold this to, the previous one. We'll take his name from now on.
Shubhodip.
Okay, so Subhadeep now got super mad and did built this circuit. Now Subhadeep, you have to respond now. Okay, so let us see whether you are able to fix it using this. Okay, so now again, when we are trying to solve this, okay, so what happens is that again we'll have two cases to solve. So here it is I1 and here it is IB. So again we'll have similar case 1, in which IB is much smaller than I1, then it simplifies and you can obtain Vx, implies Vx equal to VCC times R2 divided by R1 plus R2. Okay. VCC equal to Vx equal to VCC times this thing. This is very straightforward. If not, then you go to case 2, where you redraw with RTH, okay, and VTH, and you draw this amplifier like this, because you have to find this IB. Okay, so this is RE, and of course you have, this is VCC, this is RC, and this is V out. Okay, so you have to find this IB over here. Oh, RTH, I don't know why this got. Okay, you have to do this. Now, what is RTH? VTH equal to same as before, R2 by R1 plus R2 times VCC, and RTH equal to R1 parallel R2. Okay, so this is what you have, and then V out is given by this, now this thing. So now here, you have to use that iterative technique to solve for the amount of the IB. Okay, so whatever is IB here, it is going to be beta plus 1, right? IB will flow here, and thereby you can write beta plus, you write a KVL in this loop. So KVL in this loop, you can apply KVL in this loop, and then VTH equal to IB times RTH plus VBE, VTH equal to IB times RTH. So in KVL in that loop gives you KVL in the loop gives you VTH equal to IB times RTH plus VBE plus beta plus 1 IB times RE. Okay. So this is what is there, and you can solve this iteratively to obtain the same technique that can be you can do that to solve for the solve for IB, and once you obtain the IB, then you can easily find out what is IC and thereby what is the output voltage. Okay, so now let us see how this is the case 2. Okay, now we will do Subhadeep modified this circuit. Now Subhadeep, you are there? Where is
Yes,
he? Is he
I
present or
am
not?
here. Yes, I'm
Where is
present.
he? Okay, you are there. Okay, good. So now let's take the same example a little differently. Is it? So what you did is you modified the circuit to like this. You said, you know what? I'll rip apart everything and I'll build my own circuit because I know what he has done. So R1, you chose this. R2, you chose this. RE is like this, and this is 1 kilo ohm and RC. Okay, V out. Okay, so this is what he did. Now we will again to solve this circuit, we will assume, let's assume, okay, IB and here is I1. IB is much smaller than I1. Then Vx is how much? Can you solve for Vx? VCC equal to 2.5 volts. Keep in mind we are keeping the same IS. Okay, what Shubhadeep started with. They are not what Subhayan started with. IS equal to 10 to the power minus 17 amperes. Okay, so he did this. So what do you get here? Vx equal to 900 millivolts. Okay, and assuming VBE equal to 800 millivolts, you get this voltage Vp implying Vp equal to 100 millivolts, and therefore IE equal to 100 millivolts divided by 100 ohms, which is roughly equal to 1 milliamp, right? And IE will be roughly equal to IC. And we are keeping the beta the same that Subhayan started with. Okay, and thereby we can obtain IB, and you can verify that IB will turn out to be will be small. Okay, so we can find out that IB is this thing. Okay, now when you do that, okay, what is the value of V out that you get? How much will you get? You will get V out equal to 1.5 volts. Okay. Now what is the difference between what Subhayan had and what Subhadeep has? Roughly 150 millivolts, right? Yeah, we compromise 150 millivolts, but he will go and give this demo to Subhayan and show that, you know what, you put whatever transistor you want. You go and get whatever transistor, I'll show that it stays at that 1.5. This node voltage is not going to budge from this value. Okay. And then once he does that, he tells the whole class and he makes a good business out of this and makes a ton of money. So Subhadeep, you are going to get richer. Now prove that when you change this transistor with a beta of 50 and IS equal to 2 into 10 to the power minus 17 amperes, this node budges very little from 1.5 volts. Prove it now. you're going to make a ton of money. So please do that, because that's how all these demos, when Intel and all they come up with, they give all these demos, and in the demo they prove that things work like this. Okay, Subhayan, if Subhadeep is not able to help, then Subhayan, you please pitch in and prove that when this changes, you get it does not budge from there. Subhayan, anybody can help? I see a chat there somewhere. Somebody has put something in the chat. Shruti Shreyasi said that the other one goes into. So please don't hesitate, you guys. Speak up, but not all of you together, because this is an online thing. It might get messy. So don't be shy. Speak up so that I know that you guys are participating. So Shruti, why don't you answer? Shruti Shreyasi. What happens? So when you design with this, you get 1.5 volts. Sorry, did I take the number right? Beta equal to 100. In this, to get 1.5 volt, please solve it. I think that IS that was used was, I'm looking at the numbers in the textbook. Let me put it here. To give you 1.5 volts, IS that was used was 5 times 10 to the power minus 17 amperes. So you now change the new IS to 10 to the power of minus 16 amperes, and prove that when you design with this, you get V out equal to 1.5 volts. When you change the transistor and replace it with this voltage changes. Can you tell me by how much does this voltage change? Does the transistor go into saturation? See, for me, I can keep on rambling about these things. Unless you try to help me and solve some problems and make it interactive, you won't ever learn, no matter how many times you listen to the video lecture and all. Okay, Alisha, please, Subhayan. Subhayan.
Sir, I had done with 2 into 10 to the power minus 17. Then you changed that. So
Okay, so no, because in the textbook, when I said the V out equal to 1.5 volt, this will be 1.5 volt only when IS is this much. Please verify it.
actually, when the new IS is like 2 into 10 to the power minus 17, which you have given previously, then the change is almost 0.4 volt in VC. VC changes almost 0.4 volt.
VCE or VC collector? VCE is this difference.
Yes, VCE is changes in 0.4 volt, and collector is changes about 0.6.
Tell me how, what is when you did this, so Vx equal to 900 millivolts, right?
Yes.
VB equal to 800 millivolts, correct?
Sir,
So therefore,
Sir, VB, I mean, as these things has changed.
wait a second, this crashed.
I said just wanted to know the approximation which we have made previously is still working or not. I mean, IB is less than IX.
It is happening, right? It will hold in this case. I'm pretty sure that it's going to hold here.
Hold, yes, sir. So
it is holding, right? So now VB is 800 millivolts. So the VP is how much? 100 millivolts, right?
yes.
If VP is 100 millivolts, so the current flowing IE is equal to 1 milliamp.
Yes.
right? If it is 1 milliamp and then the voltage here is going to be 1.5 volts, right? That is clear.
Yes, sir.
So if I plug in this 1.5 millivolt into, now what is the VBE if IS VT, V thermal voltage ln IC by IS. So here IS you should plug in this value. It should roughly give you 800 millivolts, which was our assumption. Correct? Does it give you that? IS of this will give you that.
It's giving 957 millivolts.
Are you sure?
Yes, sir. It's
Yes, yes.
957.
If you plug in IC equal to IC equal to 1 milliamp, right? And IS equal to 5 times 10 to the power minus 17 and VT ln of
I
this,
got
it should give you,
Just 778.
I got 796.
yeah, you should get 796. You should get 796. That's what I'm seeing in the textbook, which is pretty close to this much. So you can keep it as, that means our assumption of 800 millivolts was correct. Okay. Okay. So now when I change this with a transistor of a different beta, means I'm going to change it to 10 to the power of minus 16 and a beta of 50. Okay. That time what happens? So you have to again do iteratively solve it, of course, and you will see that this voltage doesn't budge from that value. Can you prove that? Or let's take another example which is done in the textbook. You have solved that. So let me, what the book has said that if R1 equal to 16 kilo ohms is what we had, R2 equal to 9 kilo ohms, okay, and you had this as 100 ohms equal to RE, and this is going to give you RC equal to 1 kilo ohm, and this is your V out. Okay, so now what that, as per the textbook problem, if R2 changes by 1%, that is by plus 1%, that is, I'll put it plus 1, but that is new R2 new equal to is how much is 9, 1% is 900 kilo ohms, right? 900 ohms. So it will become 9.09 kilo ohms, right? If it becomes 9.09 kilo ohms, then you can again solve it and you will see that I1 here and I1 will still be much greater than IB, but the voltage here will increase to from 900 millivolts, Vx will increase to 909 millivolts. Instead of 900 millivolts, it increases to 909 millivolts. And although this Vx increases by 9 millivolts, the extra 9 millivolt drop will almost come across this RE and it will maintain the VBE at the same value as before and will maintain IC at roughly equal to 1 milliamp and thereby maintaining V out close to same 1.5 volt. Okay. Am I clear? Subhayan, is that okay?
So is the increase 909 or 906?
Yes, sir. It's
909 is what
905.74. 905.74 it's coming.
Yeah, exactly that.
Is it
Yes.
900 and how much is it coming?
5.7.
905.74.
905.74. Okay, it doesn't matter. Okay, you pick. Where is it? Let me. So please tell me how much does it become? Vx will increase to how much?
905.7.
Okay, good. 905.74 millivolts. This 5.74, if you work out, will drop across here, across this, and thereby it will increase. Let us say it drops across here, it will increase this IE by a very small fraction from 1 milliamp. It will increase to 1 milliamp plus 50 microamps, which is roughly equal to 1 milliamp. Thereby the IB doesn't change and the IC doesn't change that much. Therefore, the V out will not budge that much. It will reduce by a very small amount. Am I clear? So what does this emitter degeneration do? So let us try to understand intuitively what this does. Suppose due to some reason this voltage changes. Okay. So now keep in mind for a transistor, let us compare this scenario with a scenario which is like this. R1, R2, like this. Let us compare this scenario like this. V out. Okay, so here it is Q1 and here it is Q2. Now let us analyze various scenarios. One scenario is this node voltage increases due to some reason. This node voltage Vx increases due to some reason. It could increase if VCC increases. It could increase if R2 increases. Right? Any of these reasons Vx can increase. This Vx increase in the second case directly comes as VBE. Okay. As soon as it increases VB, the IC is going to increase and the output is going to drop. Now let us see what happens. Suppose this voltage increases due to some reason. Then let's say it increases the VBE. Then immediately IC increases. If the VB increases, the IC is going to increase. As soon as IC increases, then IE is going to increase. So this drop here, this voltage is going to increase. If this voltage increases, then it will bring back VBE back to its original value because this has increased, so this value doesn't change that much. So the difference between this circuit and this circuit is that any reason that changes this Vx would result in the change in the current, but that current that is flowing over here will also flow through this resistor and increase this voltage, thereby maintaining this difference almost at the same value. Thereby not change, thereby keeping the current. If the VB is maintained at the same value, the current will stay at the same value. But here, in this case, I don't know why this got erased. In this case, that doesn't happen. If this voltage changes due to some reason, then the drop VBE, it will reflect directly as a VBE and it will change the current and it will mess up your output, the DC current flowing through the transistor and will mess up your output. So that is why this circuit is pretty robust to any changes in the Vx. Now let us say due to any reason the transistor is changed. Suppose Q1 and Q2. Q2 is changed, the beta changes. Okay, this node is not changing, it is the same value. The beta changes. As soon as beta changes, the collector current changes. As soon as the collector current changes, the output is going to drop. But here what happens? If I replace it with a different transistor with a different beta, the beta will change. That change in beta will reflect as a change in IC. That same IC will flow here and appropriately adjust this voltage, the VP voltage, and make sure that this VBE is not changing that much. It will bring back this to the same value. Okay. Now, the thing is that we have to now, the thing is, how do we, now the voltage over here should be significant enough, or the voltage across this RE should be significant enough that it is able to counter the change in VBE. Now you can work out, if I have an exponential relationship, EXP VBE over VT, if that is there. If VBE changes by 10%, by how much does IC change? How much does IC change? Can you please work it out? So IC1 equal to IS exponential VBE over VT, and IC2 equal to IS exponential 1.1 VBE over VT. Therefore, IC2 over IC1 exponential, right? Am I correct? Is it okay? Subhadeep?
Yes, sir.
Okay, so if VB equal to 800 millivolts, original VB was 800. So can you plug this in and tell me by how much does this change? If VB equal to 100 and VT equal to 26 millivolts, IC2 changes by how much? IC2 by IC1 is how much?
21.7.
51.7.
So it changes by a factor of 21 times. It becomes 21 times bigger, right? Am I clear? Is that right? Right or wrong? Subhadeep, Subhain. Okay, so it is 21, almost 21 times bigger. So that means if the VBE changes by only 10%, means by 80 millivolts, the current through the transistor will become 20 times bigger than what it was earlier. Okay, and this VBE change can happen due to many factors. One is R2 is changing, R1 can change, VCC can change. Okay, similarly, when I change the transistor, VBE might not change, but the IS might change, and that can change by a factor of 10, and that will change the overall IC by a factor of 10. Okay, so 10 or 15 also it can change. So these are the various. So now the rule of thumb is we have to make sure the voltage drop across this should be at least 10 times bigger. Okay, I would say no, 2 to 10 times. That means the voltage drop, as long as the voltage drop, as long as the voltage drop across RE at least 3 to 10 times more than tolerable variation of VB this circuit will be this circuit short form is CKT, is immune to bias point variation. Bias point variation. Is this statement clear? So now let us try to take some numbers. So let us say we define a tolerable variation of VBE as 10%. Because certainly more than 10% is a huge variation. I mean, you can see that with 10%, the IC changes by 21 times. If it is a little more, it is changed. So 10% variation is a tolerable variation in the VBE that we can tolerate. So now if 10% of 800 is 80 millivolts, so as long as the drop across this is roughly 200 or 3 times 80 is 240. So to more than 200 millivolts, okay, more than 200 millivolts, then the circuit, the bias point means the collector current flowing through this, and the output voltage, the VCE or the collector voltage is not going to change that much if due to variations in these different things. And we know that the variation in the R1 and R2 cannot be more than 20% because that is what is available in the market. Okay. Is this statement clear to all of you, whatever I've written, although it's written in a very any questions on this? Any questions? So now you are doing a similar experiment in the lab. So let me now highlight what is the design guideline then. So the design procedure is you decide on a collector current to give you appropriate GM and R pi. Okay. Now, based on maximum variation of R1, R2, VCC and VBE, choose IERE, which will be roughly equal to ICRE, okay, equal to 3 to 10 times the variation, 10 times variation. Okay, so but I would say 3 to 10 times variation of VBE. Okay, always translate the R1, R2 VCC variation to that effective VBE variation. So that means always translate R1, R2 VCC variations to VBE variation. Okay, because R1, R2 variation, R1, R2 VCC variation will change Vx, thereby changing VB. So consider it that way, because if you consider this scenario, so this is R1, R2 VCC, this is node X. Now here, if I have no resistor, this variation of R1, R2 VCC would translate to a VBE variation. And of course, the transistor will have its own VBE variation. So that's why we say that always translate, and that's why we have the statement 3 to 10 times variation of VBE. Now for your lab, where VCC equal to 5 volts or 12 volts, choose ICRE of roughly, I would choose 500 millivolts or 1.2 volts. Okay, because this voltage is very high, you do not follow this criteria. Please do not follow. For lab, do this. If it is 5 volts, choose ICRE equal to 500 millivolts. If it is 12 volts, you choose 10% of that. But if VCC equal to 2.5 volt or less, which is typically the case typically in most electronic circuits, most modern electronic circuits, choose ICRE as mentioned in the beginning, in beginning of point number 2. Is whatever I have written, is it clear to everyone? Subhadeep, Subhayan, Harika, please tell me if there is any question, I will appropriately correct it. Is that clear?
Yes, sir.
Okay. Okay. Now you do this, and after this, what you do is point number 3, calculate Vx equal to VBE plus ICRE with VBE equal to VT ln IC by IS. Okay, then 4, choose R1 and R2 so as to provide appropriate Vx. Okay, so this is how you are going to design it. Okay, now I want to also introduce one more thing here quickly without getting into the amplified topologies so that you can do the lab properly, because you have already started this in the lab, right? Am I right?
Yes, sir.
Okay, so you have started this in the lab, and so now in the lab what you are doing is, now one more thing that is of critical importance is, what supply voltage are you using in the lab? Tell me that.
So 12 volt.
12 volt.
12 volts. So then keep this at 1.2 volts. Okay, so this is 12 volts. Now, one important thing, when you are building a circuit, the battery life of the circuit has to be as large as possible, because you yourself hate to change the battery every few days, right? So you want as if the battery life should be infinite. Now, when we analyze this circuit to find this node voltage Vx, we always, the case 1 was much simpler to analyze because IB, I1 and IB. IB is much smaller than I1, then it becomes simpler to analyze. But that means that you are burning a ton of current in this R1 and R2. Okay. So if IB is much smaller than I1 implies you are wasting current slash power to generate Vx. So as a designer, you should not make IB much less than I1, implying make IB almost equal to, or IB should be comparable to, I would say if this is I2, IB should be comparable to I2. Okay, this will save power in bias branch. Okay, this is the bias branch. The bottom line is biasing circuitry should be made as low power as possible. This is an important thing. This will save you a lot of things. So if you see your cell phone, ton of analog circuits are there sitting in there, tons of them. Okay, you will be amazed. I can show you some pictures of some of those things. So I will, let me see if I can find out. I'll show you one picture of so let me share the screen with all of you. Okay. 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 So, um, do you see the screen?
Yes.
Okay. Okay. So this is a two-chip solution. Okay. Let's forget the left part of the chip. Okay. We will get into that. We will show that. This is a four-channel receiver for MIMO reception. Okay. Multiple input, multiple output with multiple antennas. Okay. And they have split it up into two chips because it was difficult to handle in one chip. Now you see that this part in the center is all digital circuits. These things work. See, all these things are, the analog circuits will be very, very regular. They will be very, very regular here. Now imagine there will be roughly 20,000 transistors. Digital here, there will be probably a million transistors here. But analog circuit, there are very few transistors, but very difficult to design. You see that how things become. This is a phase lock loop which generates the clock, which is again an analog circuit. Okay. So now this is mostly an LNA and a mixer, and then you have another receiver over here, and this is an antenna, on-chip antenna. LNA mixer, and then there is an IF amplifier. This is an analog circuit. This is a detector, probably a peak detector or something, and this is a baseband circuit. It could be an analog to digital converter, and you get digital outputs. Okay, so now these circuits have to be biased, right? And you will have a bias circuit sitting in some corner. Probably they will be sitting somewhere here. This might be a bias circuit or something, and the currents will all be distributed everywhere. Now the bias circuit should be burning as little current as possible. Okay, so that is the bottom line. And if your bias circuit starts burning current, because the bias circuit is only generating the voltage necessary for the transistor to work, it is not doing any useful thing other than generating this Vx. Most of the useful thing is done by this thing. This guy is sitting here taking your signal and amplifying and giving you all, doing all the work. Why do you want to waste, not give this guy more power than this guy? Right? So this guy is just setting this voltage and telling it, okay, now you are ready to go. Okay. So this guy, we should minimize the power consumption of this circuit. So I hope this statement is clear to all of you. Okay. And I hope this will facilitate you in analyzing your circuits. Okay. So now I got some feedback from the lab things that you guys are having problems trying to understand certain things that R1, R2. I hope you guys have done the frequency response and you know what is Bode plot, right? Or no?
So we did it in the lab, but not in theory.
How come in network theory, how come it is not done? In networks, you should have Bode plot, poles and zeros. They have not been analyzed.
No, sir.
Okay, so I don't know how I'll do that. I don't think I can get into poles and zeros so quickly. It will take me until end of February to get into that point. So what you have to do is you want you want two things. First of all, this transistor Q1, it should be robust to variations in these parameters, right? So that's why you go for emitter degeneration. Okay, but you do not want. Now, what did you study in the class? If I tell you now, if I want to draw the part of the circuitry which is relevant for amplification, do I need to draw this? Do I need to draw this? Or if I tell you find out the gain of this amplifier, so what will you do? You would ideally try to draw the small signal model of only this one, right? And say that V in is applied here because that is what is actually of relevance, because this part is generating the bias. So V in is generating applied here and you get V out. I'll tell you find out the gain of this amplifier. So what did you learn till now? The gain equal to absolute value of the gain equal to effective GM times R out. Now, you guys tell me, what is the effective GM of this one? Isn't it GM1 divided by 1 plus GM1 RE? Remember, we did one topology where there is a resistor over here, the effective GM was given by this. Okay, what is R out? RC is R up. Parallel, R down is how much? GM1, RO1, RE, which is, this is roughly equal to R. Okay, something happened. Are you, can you hear me now?
Yes, sir.
Okay. So this number R down will be much greater than RC. RC will be 1 kilo ohm probably in the lab. So this will turn out to be RC. So what is the gain then? The voltage gain, the absolute value of the gain equal to GM1, and GM1 RE will be much greater than 1. Typically this will be 10 or 20 and this is 1. So this will be roughly equal to RE. Okay. So it will turn out to be, so your gain will therefore be given by, your gain will therefore be given by RC by RE. Okay. Not a very good gain. Probably 2, 3, 10, you'll get a gain of 10 probably here. If RC equal to 1 kilo ohm and this is 100 ohms, you will get 10. Okay, not a very good number. But what is the gain what is the maximum gain I can get if I had just this transistor here? If I had this transistor, if I built, one of you built this, what is the gain for this one? Isn't it equal to GM1 RC? Now, if it is GM1 RC, but what is the problem of this? As soon as you change the transistor bias point, it gets messed up. So you want the gain of this circuit. So ideally, I want the gain of this circuit. Gain is wanted. This is gain I want, but I want, this is robustness is also needed. Robustness is needed. Now, how will I modify this circuit so that I get a gain of this and I get the robustness of this? What will you do?
We will use bypass capacitor.
Yeah, exactly. So that means you are going to put a capacitor over here. What does this do? It won't let any DC current. It will set the bias point. So the robustness is due to the biasing. So the biasing is undisturbed by this capacitor. But when I do the small signal, I want to amplify the signal. So I should not have this resistor. So that means the signal should completely go to ground here. Any variation in the voltage here should be, this node should be an AC ground for all my practical signals of interest. So this is what we do and thereby get the huge amount of gain. We get the gain of this circuitry, but the robustness of this circuitry. Am I clear with this? Any questions on this? Any questions? Okay, so that is the reason why we have this capacitor. Now, this capacitor gives you a zero in the system. Okay, now let us try to understand without going into equations. How do we get a zero due to this? Okay, so let's try to understand. So now we have built a circuitry. Let's take a 2 minutes break. Okay, let's take a 2-minute break. Okay, yeah, sorry. Talking for so long, your throat gets dried up. Okay, so now uh, you have this circuitry here. Now, you must have in the lab there you might be shown that this is giving you a zero, right? Am I right or no? Yes or no? Are you getting poles and zeros in this system?
Sir, in the last lab, in the last semester in Introduction to Electronics, they showed us the equation through which we get the zeros and poles.
Okay, so you get the zeros, the equations, right? See, equations are, we are also engineers. We should try to physically understand what is the meaning of that equation. Now, what is the meaning of zero? Can you tell me? And what is the meaning of a pole? Anyone? What is the meaning of a 0? The output is 0, right? 0 for certain input. Certain input at that frequency. Okay, and now don't confuse the frequency with a sine wave. You have to consider everything here. You have sigma axis and you have j omega axis. All of you think that say frequency is a sine wave, means that means is it on the sine wave? I can have an exponential signal also. The signal on this x-axis is denoted by an exponential signal. Okay, or if it is on the left side, it is minus sigma t, whatever. This is an exponential signal. So x-axis, the signal is denoted by an exponential waveform. On the y-axis, it is denoted by a sine wave or a cosine wave or whatever. Okay, pole is when the output is infinity for certain input at that frequency signal. So that means it could be if sigma real, if the pole is 0, that means you have to give an exponential signal to see that infinity. If the 0 is a real 0, that means you have to give an exponential signal to see that 0. Okay, that means if I give, suppose I'm giving an input over here, right? So I give the input using here, okay, and I give an exponential, and now the 0 turns out to be a real 0, and let's say the 0 is on the right half plane, so it will give me e to the power of sigma t. So if I give this signal at this point, output will be 0. Okay, that is the meaning of this thing. So now let's try to understand when, now if you look at this circuit, okay, what is the circuit of relevance to analyze for the gain? We know that the okay, so what is the circuit of relevance? This is RC, this is there, RE, CE, and V in, and this is V out. Can anybody tell me when can if I give an input, under what circumstance will I get an output 0? Okay, so I'll give you a hint. Okay, suppose somebody built a circuit like this. What is the gain of this circuit? What is the gain of this circuit? Anyone?
GMRC.
What is the gain of the circuit? Will this circuit have any gain? Will the circuit have any gain? Anybody? This is an ideal current source, right? This is an ideal current source, correct or not? Now, can you
No.
change the current through this?
No gain.
Why no gain? Explain, Shubhayan.
The ideal current, I mean the current cannot be distorted in emitter, so that's why also not in collector. So no voltage output distortion we can
Exactly.
get.
So I can do whatever change of input voltage I apply. That voltage will show up here, maintain this VBE at the same value. This current is not going to get, you are going to get a 0 scenario, 0 output. Okay. So that means from this emitter, looking downwards, the resistance is infinity. Okay. Can I have that same scenario here at a certain frequency? Can this behave like an infinite resistance at certain frequency? Means there cannot be any current. So that means there will be all the current will be circulating over here. It can be. So IRE IRE equal to I SCE. Therefore, at S equal to 1 by RECE or S equal to sigma plus, this is a real. So at S equal to 1 by RECE, the current keeps circulating, it nothing can go over here. So that means if I apply, this is a real number. So if I apply e to the power of t by RECE, signal at this point, no current will flow in this circuitry, and thereby I'll get an output equal to 0, and therefore your 0 will be at 1 by RECE. Are you getting the same thing by solving all the small signal? Do you get the same thing or not? Subhayan? Alicia, what was done in the last semester? Did you get the same result?
Sir, I actually don't remember. Like,
Because you guys were writing tons of equations, right? That's a problem of analyzing circuits using equations. That is why we have to come out of that small signal model, writing tons of equations. Okay, we have to analyze by seeing how can this output be 0. So I have to mimic a scenario like this. That means I should have an impedance looking this way as infinity, and therefore I can have this infinity if all the current, the small signal current is circulating around this and nothing comes out of this. Ideally this current and this current, they should satisfy KCL. But if nothing is coming out here because this is circulating over here, then this is behaving like an open circuit. Okay, so no current flows here, and thereby you get 0 gain. Okay, so you should get this result, and when you are plotting this, this manifests in the Bode plot as a 20 dB per decade rise in the gain slope. 20 dB per decade. When you hit a pole, you will now get minus 20 dB per decade, and the slope is going to flatten out. And then you hit another pole, and the gain is going to again drop down at minus 20 dB per decade. And you should get your frequency response of this amplifier looking like this. Okay, so this 0 will be here, that frequency, and this pole will be coming as, there will be a pole associated with this as well. Okay, so I'll explain that later, it's too much. And then finally this pole is due to this at this node, and you can do it without really doing any small signal model. That is why I taught you all this impedance looking into this node, that node, and all those things. Okay, so this should suffice for your lab experiment. You should see a plot. Are you guys seeing a plot like this in the lab?
Yes, sir.
Okay, so and you can map this to this 0. Are you able to map it to this 0? This thing will map it to something else. This thing will map it to RC times the CL over here. Okay, all these are in radians, by the way. You have to, if you are doing it in frequency, you have to find those out in frequency. Okay. Now you might ask that this is a pole, why am I not getting infinite? Because this is a real pole. Obviously, you are what are you measuring when you are applying? You are applying signals over here. You are not applying signals along this axis. You are applying signals over here. They manifest not as infinite gain. Similarly, you apply a signal over here, but they manifest as a 3 dB decrease or 3 dB increase in the value. Okay. So I think when I go into frequency response, I'll go into all this detail, how they manifest and all. But at this time, I just wanted to quickly cover what should be there in the lab. So I think you should see 0 at this value. You should see a pole due to this node, due to this capacitor. You should see another pole due to this capacitor, and thereby you should see a frequency response which is looking like this. This pole will be RC times CL. This pole will be, I can tell you, right, but it's a little, so 1 over GM parallel RE times CE. Okay, so that is where the poles and zeros are going to be. Okay, so with this, I think you can do the lab experiment to some extent. Anything else in the lab that I need to cover now? Any questions so far? Okay, so now the last biasing scheme is called self-biased stage. Okay, and the biasing scheme looks like this. Here you can also have degeneration. There is nothing stopping you from having the degeneration resistor RE. So the biasing scheme is self-biased, means there is an RB which is going like this. Okay, and this is node X, this is node Y. So this guarantees that the transistor will always be in forward active mode, because this node voltage will be higher than this, right? Because current will flow like this. IC is here, IB is here. Okay, so here Q1 is always in forward active mode.
So,
Yes, please tell.
so yesterday we did the experiment for the bandwidth, and for when we had cascaded after C amplifier, we had an emitter follower, and then when we put a capacitor, the waveform overshooted for a particular frequency.
Okay.
So why was it like that? Like
Okay,
you
so again,
explained.
okay, so so there it behaves, because you have an emitter follower, it behaves in an inductive manner. So see, you can realize an inductor using a capacitor, you can realize a capacitor using an inductor, and all these things are there. Okay, so I hope, I don't know if you have studied gyrators. Have you studied gyrators in networks?
Yes, sir.
So I don't know about networks, but yeah, we had it in another
Which course?
signals and networks.
That is what, signals and network, that's what I'm talking about. Yeah, gyrators. So what is a gyrator? What is a gyrator? What
So
is a
it is
gyrator?
like we can use it to like uh, negative resistance kind of. So like inductor is converted to like at the input, if we connect an inductor, the output is a behaves like a capacitor at the output.
Exactly. So your emitter follower behaves under certain scenarios. Okay, and that scenario should be avoided if you are getting that peaking. But at this point, you cannot avoid that. Okay. Because at the board level, it is difficult to do it. It is sometimes difficult to avoid it, but in the IC level, you can avoid it. So you will have that effect. I don't think I can discuss that right now. It will become too much, because I have to introduce the concept of analyzing circuits by associating a pole at each node. Pole at each node. Okay. And zero is obtained by finding alternate paths to output. Finding alternate paths to output. Alternate paths to output. So if I introduce this concept, which I can only introduce by, and after I finish all the amplified topologies and go into frequency response, Please hold on to that. For now, assume that with a pinch of salt, and that is nothing wrong you are seeing, and it is obvious, and you will be able to do that after I get into this, which will be probably third week of Feb most likely. Okay. Unfortunately, I cannot help. Yes, there is somebody raised a
Yes,
hand.
sir.
Yes.
So I had a small doubt. For our lab, we refer to the circuit you had drawn just before this. The one we were discussing is the self-bias stage. So,
Yes, I know. This one is self-biased, but she asked me, Tanaya asked me why was they had cascaded that with an emitter follower, and you see a peaking response that happens due to some phenomenon which can be related to a gyrator concept. Okay, and in order to understand that, you have to cover these two topics, which I will do later on, not at this point. Am I clear? That's why I went into this. Okay. So now the last biasing scheme is called biasing using self-biased this thing. So this guarantees that Q1 is always in forward active mode because this voltage will be higher than this. No questions about. So therefore this junction, base collector junction, is always reverse biased. And now here, if we write all the KVL and KCL, so Vy, this is the node Y, equal to VCC minus RC times IC. Okay, because actually it is not IC in the true sense, but IC as IB is much smaller than IC. So we are ignoring that. So we write it like that. And also we can write this as Vy. This we can rewrite it if I write the KVL along this loop. KVL from ground to Y gives Vy equal to VBE, which is VBE plus VBE here plus IB times RB, which is equal to VBE plus IC RB by beta. Okay, so therefore by equating these two, IC equal to VCC minus VBE divided by RC plus RB by beta. Okay, so this is one biasing scheme. This is the third biasing scheme. So we talked about the simple biasing scheme, resistor divider biasing, and then resistor divider with emitter degeneration, which is the most robust form of biasing. And of course, there is self biasing. Here also you can do an emitter degeneration. As soon as you degenerate with an emitter, you get more robustness in terms of the stability of the parameters. Okay. So these are the three biasing schemes. Now, as I had told you, I'll also, in case of, now let's see whether for a MOSFET. Now, MOSFET, which of these will be valid for MOSFET? So we talked about these biasing schemes for BJT, right? For BJT, we had these schemes. So VCC, right? RB, and then this here RC, V out. This is one simple biasing scheme. Then we had this resistor divider, R1, R2, then RC, V out, and then finally the simple biasing scheme. Self biasing scheme. Okay. Okay, V out. All these can have with the emitter degeneration also. There is nothing stopping you from doing that. Now, based on these, looking at these circuits, which one can we do for a MOSFET? Can we do this for a MOSFET? First one, let's call this 1. This is 2. And this is 3. Can we do this for a MOSFET? For MOSFET, only number 2 is valid. Why? because the gate current is 0. So if I connect it through RB, then this will become VCC for a MOSFET. So this is not for MOSFET. If I connect gate current is 0, so that means this and these two are the same DC voltage in case of a MOSFET. If Q1 is replaced by a MOSFET, M1, then this is DC bias is the same. Here this voltage will become equal to VCC if Q1 is replaced by a MOSFET. So the only biasing scheme that is valid for a MOSFET is this biasing scheme. Okay, of course valid in discrete components. We cannot, we have not, I'll write it in cap, discussed IC level, integrated circuit level biasing schemes. As this is not part of the course, so these are totally different, and I don't think I can cover it in this course and finish the syllabus. So these will be covered in your 4th year. There is a course on analog IC design where it will be covered at IC level how different biasing is done. Okay, so MOSFET. So now this kind of wraps up both the MOSFET and the BJT biasing. Am I clear? So I think we are close to this thing. Any questions? I'll stop the recording.